Here's an interesting idea. We have discussed a lot about how the intermittency of solar and wind has to be dealt with as we keep on increasing the fraction of renewables, and hopefully someday we'll be all renewable when we hit net zero and decarbonization goals, etc. But in the meantime, the battery storage or energy storage is something that's very critical, and we have talked about grid designs, microgrids, nanogrids, and utility scale grids, and how electric vehicles can in fact put the energy back into the grid when they're not running. So this paper takes this idea a little bit further and does some modeling and calculations to project out into to 2030 in terms of energy demand, renewable fraction, EV growth, and if EVs participated into this program of giving the energy back to the grid but acting as storage devices when they are charged based on when they charge and so on. The claim is that you can actually meet the short-term grid storage demand by as early as 2030. So obviously, it involves projections, which means you have to be aware of all the assumptions that go into it. So we'll look at the model in a flowchart way to see what are the details that are going into this model, what are the assumptions that are made, and you can follow up with more details if you want to really dig into it further. I'll just read the abstract just so that we understand the concept fairly well and the numbers that the model produces. The energy transition will require a rapid deployment of renewable energy and electric vehicles where other transit modes are unavailable. EV batteries could complement renewable energy generation by providing short-term grid services. However, estimating the market opportunity requires an understanding of many socio-technical parameters and constraints. We quantify the global EV battery capacity available for grid storage using an integrated model incorporating future EV battery deployment, battery degradation, and market participation. So you need to find enough EV owners to participate into this program and incentivize them with policies and other leverages. We include both in-use and end-of-vehicle life use phases and find the technical capacity of 32 to 62 terawatt hours by 2050. Low participation rates of 12 to 14% are needed to provide short-term grid storage demand globally. So you don't even need 50% of the people participating. Could be as low as 12% or as high as 43% depending on various factors that we'll look at. Participation rates fall below 10% if half of EV batteries at end of vehicle life are used as stationary storage. So if the vehicle is phased out for whatever reason and the batteries are removed and reused, then obviously they are not moving with the car, so they can be used as stationary storage. Short-term grid storage and that stationary storage could drop the participation required to 10% of EV batteries. Short-term grid storage demand could be met as early as 2030 across most regions. Our estimates are generally conservative and offer a lower bound of future opportunities. So they say they have done these calculations and they've been very conservative in estimating this, and that in reality this could be just a lower bound of future opportunities, which means this could scale up much more than what is reported here. The stated energy policy scenario, so model any projection for the future needs scenarios. The stated energy policy scenarios incorporates existing EV policies only, while the sustainable development scenario is compatible with the climate goals of the Paris Agreement and sees a larger EV fleet. So this is about the 2 degrees C and 1.5 degrees C warming targets by 2100 with 67% probability, which will require a larger number of EVs to be brought into the market along with other technological promises on carbon capture, bioenergy, and so on. The scenarios include two battery chemistry scenarios to capture different technological paths. One dominated by lithium nickel cobalt oxides, so those are the anodes which give the electrons for producing electricity, X denoting manganese or aluminum, so nickel manganese cobalt or nickel cobalt aluminum, and another dominated by lithium ion phosphate or LFP. Market shares of NCX and LFP batteries are assumed to reach 98% and 2% in the NCX path by 2050 respectively, and 40% and 60% in the LFP path. These are assumptions and obviously necessary for future projections, but you have to follow up on what that means in terms of actually meeting those scenarios in reality. The model used, just to read off, we'll also look at a flowchart in a minute. We developed an integrated model to quantify the future EV battery capacity available for grid storage, including both vehicle to grid and second use. We will see what this means. Basically a recycling of the batteries from the vehicles into direct use for other applications. The supplementary material provides more details which you can look up. The integrated model includes 3 sub-models. The first one, a dynamic battery stock model to estimate total future EV battery stock and the retired batteries as at vehicle end of life. This model considers EV fleet, i.e. battery stock development and EV lifespan distribution, as well as future chemistry development. So a lot of assumptions there in terms of where the future is headed, including how the EV market shares by chemistry will work. An EV use model which includes behavioral factors such as EV driving cycle and charging behavior, so charging power, charging time, and the frequency of charging. Depending on your range anxiety, you may charge very frequently, or those who are not so anxious may recharge the batteries much less frequently, for example. Based on daily driving distance data for small and mid-size large battery electric vehicles and hybrid electric vehicles, a battery degradation model based on the latest battery degradation test data to estimate battery capacity fading over time under different EV use, battery chemistry, and temperature conditions. So obviously winter charging, so high latitude charging problems will be very different, for example. Model framework linking EV model, EV use model, battery degradation model, and dynamic battery stock models. So you have to see the legends for use of colors, which I have taken out here. Square white boxes indicate model outputs. Please see details of the model framework in the methods section. U.S. Department of Energy, U.S. Department of FASTSIM, Future Automotive Systems Technology Simulator, National Renewable Energy Laboratory, and International Energy Agency, and State of Health are the abbreviations used here. So I won't go into the details. So there is a EV use model which looks at driving distance, driving cycle, charging, battery state of charge, battery temperature, and battery degradation model from the National Renewable Energy Lab uses the degradation model including calendar life, cycling life, battery degradation under different driving and temperature conditions, dynamic battery stock model with various factors, and they all feed into and feed back among themselves in terms of capacity per battery in use, capacity per retired battery. So here the model and yellow colors are parameters or scenarios, so data source or assumptions are shown in the blue parenthesis. So vehicle to grid model, you look at demand for driving from International Energy Agency report. Vehicle to grid participation rate of 0 to 100% is used to look at technical vehicle to grid capacity, actual vehicle to grid capacity. In the second use model, you are using capacity of retired batteries and retired batteries per year to derive a second use model. So it depends on collection rate, repurposing rate, so state of health, second use utilization rate, which goes from 0 to 100% as a sensitivity. So briefly, some of the results: total technical capacity for EV batteries and comparison to grid storage demand in different scenarios. So this is nickel, cobalt, and then manganese or aluminum, as we said. Technical capacity in terawatt hours So we are here looking at years 20, 30, 40, and 50. So technical capacity, supply of second use, and vehicle to grid. So here we are in 2040 increasing to 2050 here. So these are storage lab conservative scenarios and storage lab optimistic scenarios. IRENA scenario transforming energy, IRENA planned energy scenario. So basically various scenarios give you various ramp up rates going from 2030 to 2050 for STEP NCX, stated energy policies, sustainable development NCX, which requires much more technical capacity just because number of EVs will be very different in terms of participation for vehicle to grid and second use. Okay, just remember all the assumptions. For the STEP LFP and Sustainable Development LFP, lithium phosphate, you have numbers that are slightly different. You can see here. Very hard to know the difference here, but here you can see that this one is above 60 here and is almost 20. So similar here, but here slightly less for the STNCX compared to STLFP, but these depend on various assumptions of future chemistry and future fractions of LFP versus NCX, 98% versus 2%, and so on and so forth. So just take them for what they are worth. Just remember that the idea here is to see if there is a practical possibility of using EV batteries either during the vehicle use or after its life to use as short-term storage to meet the grid storage requirements. This is global available vehicle to grid capacity in 2050. Technical vehicle to grid capacity. Hatched bars indicate the capacity limits due to key factors, and blue bars the technical vehicle to grid capacity. In B, real world vehicle to grid capacity as a function of participation rates. Results are shown for these various scenarios and so on, which you can look up in their supplementary material as well. So global theoretical battery stock capacity in 2050 in terawatt hours, battery degradation, hybrid electric vehicles, driving demand, and technical vehicle to grid capacity for various scenarios of stated policies, nickel, cobalt, lithium, and sustainable development goals. Main thing to remember is that if we stick to the mitigation adaptation policies and strategies and implementations to sustainable development goals, Paris Agreement, then we'll have much more theoretical battery stock capacity by 2050. This is almost more than double. Here you are in the range of 70, here you are over 140, and based on the participation rate, the grid storage demand is going to be in this range, and this is the STEP NCX scenario, and this is a Sustainable Development NCX scenario, and this is what is the optimistic scenario, saying as early as 2030, if participation rate is high enough, then you could meet the short-term grid storage demand on this idea of using electric vehicle batteries. This is availability of second use capacity, similar idea, global technical second use capacity in 2050 for various scenarios. So annual addition and cumulative, and how they depend on second use utilization rate as opposed to participation rate in here. So vehicle owners have to participate here, and end of life batteries have to be used here at various percentages. Again, you can see that the optimistic scenarios of sustainable development will get you potentially as early as 2030 to meet the grid storage demand estimated for 2030. Finally, total actual available capacity under various conditions in STEP NCX scenario in 2050. Blue, white, and red colors depict minimum, average, and maximum values. So you are looking at vehicle to grid participation rate and second use utilization rate. So you are here at the minimum, you are in the average range here as you get to whitish colors, and here you are in the maximum values. So these are the numbers for the the available grid storage 6 terawatt hours to 32 terawatt hours. So if the participation is high and second use utilization rate is high, you are reaching maximum capacity of 32 terawatts. If you're a minimum on participation rate but maximum on utilization rate, you are reaching here somewhere around, let's say, 10 terawatt hours, and on this axis you are a little bit lower on the scale. So utilization rate, second use utilization rate, is very important as well. Do I want to read the discussion? Well, let's go ahead and do it. Previous research has suggested that large EV fleets could exert additional stress on grid utility. Example, if the majority of EVs are charged at grid peak time. We already looked at this, saying that if charging is planned properly, in fact, utility rates can be reduced by adding EVs as part of the solution. Our findings reveal a different perspective that EV batteries could promote electricity grid stability via storage solutions from vehicle to grid and second use applications. We estimate a total technical capacity of 32 to 62 terawatt hours by 2050. This is significantly higher than the 3.4 to 19.2 terawatt hours required by 2050 in IRENA and Storage Lab scenarios. IRENA is the International Renewable Energy Agency, and Storage Lab scenario is another group that provides the scenarios for the future on energy demand, storage demand, etc. The real world capacity depends on participation rates for vehicle to grid and utilization rates for second use batteries. Participation rates may vary regionally depending on future market incentives and infrastructure, along with other factors. So people have to have places to go and provide storage, act as storage facility, and incentives have to be there so that they can then recharge when they want at good rates. The STEP NCX scenario presented in figure 5 has the lowest technical capacity, 32 terawatt hours, compared to 62 terawatt hours in the Sustainable Development Lithium Phosphate scenario, which already easily meets requirements at participation rates of 40 to 50% for vehicle to grid, with around half second use batteries used as stationary storage. At a regional level, even lower participation rates may still contribute significantly to grid stability. Overall, EV batteries could meet short-term grid storage demand by as early as 2030 if we assume lower storage requirements from the literature and higher levels of participation and utilization. By 2040 to 50, storage demands are met across almost all scenarios and even low participation and utilization rates. Very optimistic message. Other factors remain in terms of all the limitations that we have already talked about. Market penetration of EVs, costs, range anxieties, precious strategic metals and their supply and their sustainable contribution to the mitigation, decarbonization scenarios, and so on. So obviously you can read up more with all the additional information that is provided in the paper and especially in the supplemental material, especially the model details. Okay, so I'm going to leave it here.